All right, so 39, if I look at sine divided by 1 plus cosine, I see that stuff over 0 is going to be a problem. So I set the denominator equal to 0. And so that gives me this, which gives me cosine equal to -1. Well, when does that happen? Well, I know that cosine is x, so I'm looking on the unit circle for when the x coordinate is -1. So it's going to happen right here at pi, at 3 pi, so at any odd value of pi. So in other words, x is not allowed to be any 2n plus 1 pi, because mathematically 2n, any multiple of 2 is even, like 2, 4, 6, 8. And then 2n plus 1 is how we represent an odd number in mathematics, either 2n plus 1 or 2n minus 1. It just means you're 1 in front of an even number. So this would represent an odd. So an odd integer times pi is not allowed because it will make the denominator 0. X-intercept is where y is equal to 0. I set it equal to 0. The only way a fraction is equal to 0 is if the top is equal to 0. But sine is y, so where is y? 0 on the unit circle? Well, I see that that happens here and here, so that's going to be any n pi. So 0, 1, 2, 3, 4, and etc. is just going to keep on going back and forth between these two values. And remember, n can be any integer, so it can also be 0 or -1, -2, out as far as you'd like to go. So these are going to be where all of our x-intercepts are. Y-intercepts are where x is equal to 0. If you plug in 0, I think you'll see 0. That's just one of these values. Then vertical asymptotes, again, where the denominator is equal to 0. You see we've already done this. That's just where 1 plus cosine is 0. And we got all those odd values. Remember, all those odd values of x, what we don't want. Well, now we know the reason we don't want them is because that's where all of our vertical asymptotes are. Horizontal asymptotes, we're asking, as x goes out to infinity, in the long run, does this settle down? Well, no, that oscillates and that oscillates, so it never settles down to anything. Now we're ready for increasing and decreasing. So I take the first derivative and find out where it's 0 or undefined. So when I take my first derivative, I get this from the quotient rule. Well, then we end up distributing. So here I distribute that, and I multiply this together, and I end up getting cosine plus cosine squared sine squared. But we know that sine squared plus cosine squared simply equals 1. So all that in yellow is just equal to 1. So I have 1 plus cosine over 1 plus cosine squared. So one of those cancels out and gives us that for the derivative. Well, where is it equal to 0? Well, nowhere, because the top would have had to have been 0, and that doesn't happen. Where's the derivative undefined? Well, again, all these odd values of pi. So all those odd values of pi are going to be my vertical asymptotes. They're going to partition our interval. And notice that this derivative is always going to be positive, because the biggest this ever is -1 in size in terms of being negative. And that's where vertical asymptotes are. But all the rest of the time, this is positive and this is positive. And so that means that my function is increasing everywhere on its domain. So everywhere in its domain. So it's increasing inside of here. I guess I should be really careful and say increasing on every interval in its domain, So remember, because we have to, it's going to be this interval, that interval, that interval. So all these intervals of length 2 pi that we have, the function is going to be increasing. If we come over here and we look at concavity, we take a second derivative. Also, we notice that since it is increasing always on its domain, then we're not going to have any local mins or maxes. Second derivative, before I take its derivative, I'm going to pull this up top as a -1 power. So when I take its derivative, it's easier. I just get -1 stuffed to the -2nd, and then chain rule to pop this guy out. So that's why we end up getting this. So where's it equal to 0? Well, when the top is equal to 0, but again, sine is y, and it's going to be 0 here and here. So it's 0 at pi, so it's going to be at any integer value of pi, right? So it's 0 at pi, at 2 pi, at 3 pi, and then any of those negative values. So all of those become our possible inflection points. But then when we look over here, where's the second derivative undefined? Well, does that look familiar? That's that thing that we've been doing over and over again. It's just the vertical asymptotes of the original function. But note that this second derivative, sine is positive up here, and it's negative down here, and the bottom is always positive. So it looks like on our interval of 2 pi, half the time it's going to be concave up, half the time it's going to be concave down, and every time it changes sign is going to be an inflection point, right? So we see right here that we change from concave down to concave up. That's an inflection point. Concave down, concave up, inflection point. And so now we could graph that sucker and really see all the algebraic analysis that we did and why it is what it is. So this would be a case where you really would, I think in this class at least, to be able to graph that thing, but let the algebra talk to the graph and vice versa. All right, last one. Spread of a rumor. We're using the following model, which looks like this. That's what's called a logistic model, a logistic function. Has a very common shape. I don't know if I drew it out. That very common shape looks like this. Boop, boop. It's when you plug in 0, you get 1. Looks like this. It has a nice carrying capacity up here. For this case, it has a carrying capacity at 1 because we get up to 100% of the people. So when is P equal to 1/2? I ended up getting this. So you just set P equal to 1/2, and then you do some pre-calculus to get there. Where are the inflection points? I take the first derivative to get this. Notice it's always positive, which we see in the picture. And then the second derivative, we just had to do the low d high minus high d low over low squared, which gives me to the fourth. And then we do something similar to class where we view it as two big terms separated by a minus, and we pull anything constant out front. So we pull first, I'm going to pull this orange piece out front. I'm sorry, pull the yellow piece out front, and that cancels with 1 on the bottom. And then from there, we can see that we could further simplify if we had to. But we don't. What we end up doing is we say, look, I'm just going to go ahead and leave it like this. And if I want to know where that thing is equal to 0, I would set the numerator equal to 0 and solve. And I end up getting the natural log of 2a over k. And that's going to be my inflection point. Natural log of 2a over k. That's going to be that point of greatest increase or greatest decrease. Yes? So there you go. Good work. And we'll see you next time.